Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use Newton's law of gravity here. So what we're going to do here, what we're looking at is I've got a picture of the Earth here and this satellite. Now this is not to scale obviously, but what we're going to do is we're going to take a look at what's called the Geosync orbit satellites. So for example, for those of you who have cable TV or satellite TV, your satellite dish should point pretty much due south and up in the air at a certain angle, maybe 50 degrees or 40 degrees. I forget the actual angle, but it's not important for this discussion. And that's because those satellites are in what's called a geosync orbit. They orbit right above the equator. And if you're in the northern hemisphere of the Earth, the satellite, this would be like the angle. This is why these things have to point up, into space. But anyway, so these satellites orbit over the equator, and geosynchronous orbits mean that they don't move with respect to the ground. So whatever part of the Earth they're above, they're always above that, and that's why you get a continuous reception. So what we're going to do here is we're going to calculate this distance here, which is how high off the surface of the Earth those satellites need to be in a geosync orbit. Right now, if you were looking at this problem from this perspective, like from straight above, what you'd see is the satellite orbiting around in a nearly perfect circle. And then here's a kind of a picture of the Earth here. And what we'd be looking at, again, if we're looking from this perspective, the very top of this would be the North Pole. You can probably barely see it here, but I put a little picture of Santa Claus here to represent that. And what we're going to do now is draw a free body of the satellite. So the gravitational force on the satellite in this picture would be this way, and I'm going to draw that in black. Right? And that's the force of attraction between the satellite and the Earth. I can go ahead and put a gravitational force on the Earth if I want. Right? But again, my free body here is going to be of the satellite. And it's important to realize the acceleration direction of the satellite. Because the satellite is moving in a circular path, the acceleration is a centripetal acceleration and is therefore in this direction, because remember, centripetal acceleration points towards the center of curvature, which would actually be basically at the geometric center of the planet. This force is calculated by Newton's law of gravity. Right? The gravitational force, remember, is equal to the gravitational constant times the product of the masses over distance squared. So looking at this free body, this is the gravitational force. And if we're to write a Newton's second law equation for it, sum of all forces equals mass times acceleration. And I'm going to go ahead and do left positive because my standard rule of thumb, identify the acceleration direction, call that positive. Now when we sum forces acting on the satellite, this is it. That's the only force. So we've got the gravitational force, which I'm going to just use Newton's law of gravity to represent, m1, m2 over r squared, where I'm going to let m1 be the mass of the Earth. And that's going to equal ma. So this mass is going to be the mass of the satellite. That's the one I'm calling mass 2, times a. Now let me back up and talk about that acceleration again. In this example, that acceleration is a centripetal acceleration. So if we want, we can write it v squared over r. So this is what Newton's second law has to say about this problem. Now, you'll notice that the mass 2's divide out. This radius will kill one of these. So I'm going to go ahead and rewrite this equation. We're going to have g times mass 1. Now this is going to be mass of the Earth in this example, over r is equal to v squared. Now, you'll notice we don't know the r. The mass of the Earth here is something we can look up easy enough. G is a gravitational constant. We can look that up easy enough as well. But we don't know v, we don't know r. So this equation has two unknowns, and that means we need another equation. Now, we've written the only Newton's second law equation we can write for this problem. We might try to write a work energy equation, but as the satellite goes around in a circle, this is a constant speed problem, and it's a constant height problem here. There's no changes in potential or kinetic energy. The work energy theorem just isn't going to help us here. So we got to find some other different, I'll say, set of physics to write an equation. Well, the other equation we can write comes from the motion of the satellite itself. So what I'm going to do is I'm going to try to make myself a little more room here. I'm going to take this stuff and shrink it down a little bit. Give myself a little room, kind of store it. And what I'm going to do now is I'm going to study the motion of the satellite as it goes around the Earth. And for those of you who have either had me in class or been watching my videos, you know my favorite way to study the motion is via a velocity graph. So I'm going to sketch a graph. However, rather than velocity, in circular motion problems, the velocity is constantly changing in direction. So I'm going to put, rather than the velocity vector, right, we're going to use just the magnitude of the velocity, which I'll just call v. So what we're going to actually graph here is speed against time. The speed of this object as it goes around here would be constant. So this graph might look something like this. And I'm going to graph it just for one time period here, one revolution. The time for one revolution has a special name. It's called period. So rather than putting a little t, I'm going to put a big T here, and that's going to represent the period, the time for the satellite to go around once. Now, this area here gives the distance that the satellite travels. And because this is one circumference, that distance can be written 2 pi r. And that's going to equal this area, which is going to be the speed of the satellite times the orbital period. So the period is something we know, right? The period is 24 hours. And that can be written in seconds, no problem at all. I'm not going to do it right here. So in this equation here, this is a known value. And then we have another equation now between r and v, and I look over here, r and v. And again, what I want is the r. So I'm going to solve this for v. Solving this equation for v, we're going to get 2 pi r over the period t. Oops, I said over, and I multiplied over the period t. And I'm going to take this now, and I'm just going to sub it into here. So the new line is going to read g times mass 1, that's mass of the Earth, over r, equals v, which is 2 pi r over the period squared. And what we want to do is solve this for r. Now, if I multiply both sides by r, and if I look at on the right, here's an r squared. I'm going to put r cubed. And what we're left with here is going to be 4 pi squared from 2 squared and pi squared over the period squared. And then we'd have times r squared, and I went ahead and already multiplied. Whoops. And if I'm going to do that, I guess I should multiply both sides so that they cancel over here. And I'll go ahead and multiply it here. And then over on the right hand side we'd have r times r squared. That's going to give me the r cubed, and then 2 pi squared. There's your 4 pi squared over period squared. Okay, so the resulting equation we got here is gm is going to equal 4 pi squared over the period squared times r cubed. And now all we have to do is put in numerical values for these. And I'm going to need a little more room here, so I don't need this picture really anymore. I'm going to get rid of this. And the new equation now is going to read r cubed equals, let's see, we'd have to multiply by the period. Oh, and you know, I missed a little algebra step. That was period squared there. So if I want to solve this for r cubed, we're going to have to multiply by the period squared. So we're going to have big G, big M, period squared over 4 pi squared. And putting in values here, and I'm going to put NCU for note consistent units. This is going to be 6.67 times 10 to the minus 11th for the gravitational constant. The mass of the Earth is around 6.2 times 10 to the 24th kilograms. The period is 24 hours, and there's 3,600 seconds in an hour, so that needs to be multiplied by 3,600 to convert that to seconds over 4 pi squared. So what I'm going to do here is I'm going to take a moment and solve this for r. I got to double check this mass here. That might be a 6.4. My memory is not as good as it used to be, but I'll check the mass and do the calculations here. But there's no point in doing increasing video length to do that. So stand by. Okay, I'm back. So here's what I did here is I first looked up the mass of the Earth. That was just 6 times 10 to the 24th kilograms, not 6.4. Sorry about that. And also another little thing I caught here is I forgot to square that before I put that in, because that's the period squared. And when I solved this for R, I went through and did it a couple times. I got about 42 times 10 to the 6 meters. And I think that that's pretty sure that's right, because I remember that this distance ends up being about 7 Earth radii. I always remember that. I don't know why. And the radius of the Earth, if you look that up, that's about 6.4 times 10 to the 6 meters. And then you'll notice that this is just a little less than 7 times. This value is a little less than 7 times that value. So I'm pretty sure that's about right. Now again, this R that I found is the orbital distance. That's the distance from here to here, from basically the center of the planet to the satellite. I'm not going to do it right now, but if you wanted this height, you would just subtract off the Earth radius. So I hope this video helps demonstrate how to use Newton's law of gravity. Have a great day.